we've looked at how to combine capacitors that are in series with one another. What we're going to do now is look at how to combine that are in what we call parallel with one another. Okay? So let me draw a picture out here for you. This is an example of a parallel circuit. I have my two capacitors again, but notice this is not drawn the same way. These capacitors are most definitely not in series with one another. There's branch points, between them, and so they can't be in series, all right? But these two capacitors are in parallel with one another. And basically, two elements in a circuit are in parallel if they start and they end at the same branch points. So think about this capacitor here. I like to think of the line that's coming out as part of the capacitor. So this line is part of the capacitor, and this line is part of the capacitor. And then for this one, I think of this whole line as being part of this capacitor as well down here. Well, I want you to notice both of these capacitors, they start and they end at the same branch points. So here's a branch point. Well, the end of this capacitor is at that branch point, and the end of this capacitor is at that branch point. And then if I go to the other side, the sides coming out of the capacitor on the opposite side, it ends here at this branch point, and this one comes together at the same branch point. So these two guys are in what we call parallel with one another. And the question we're trying to answer is, what is the equivalent resistance of two capacitors if they are in parallel? Now, let's remember some basic things about potential. Since the potential doesn't drop really as we go across the wires, all right, that means that the top plate of capacitor 1 and the top plate of capacitor 2 both have to be at the same potential as the positive terminal of our battery, right? Because they're connected to it just by wires, ultimately, all right? Well, the same thing is going to be true for the bottom plates. Both of the bottom plates are connected to the negative terminal of the battery. And so they're going to have a potential value that's equal to the potential value down here, okay? And so what we find then is that both plates of the capacitors are going to be at the same voltage as the positive and negative terminals of the battery. And what this means then is that the voltage drop across both capacitors is going to be equal to the voltage drop from the positive to the negative sides of the battery, right? In other words, the drop across the battery, the potential difference from the negative to the positive terminal of my battery, that's going to have to be the potential difference across this capacitor, and it's also going to have to be the potential difference across this capacitor. So we could actually put that the potential drop across those is just equal to the potential of the battery, right? Okay, but now here's the thing. They both have the same potential drop, right? But they have very different capacitances. And what this means then is that if they don't have the same capacitance, then they can't have the same amount of charge. In other words, capacitor 1 is going to have a total amount of charge on it that we call Q1, and capacitor 2 is going to have the total amount of charge on it that we're going to call Q2. These two things are not going to be the same if these two capacitors don't have the same value, because delta V over, or C delta V for this one isn't going to be equal to C delta V for this one. All right, and that's the relationship between the charge and the capacitance and the potential, right? And so we could write out then that, well, Q1, the charge on capacitor 1, it's going to have to be equal to its capacitance multiplied by the potential difference across it, right? And similarly for capacitor 2, the charge on capacitor 2 is going to have to be its capacitance multiplied by the potential drop across it, which is, again, the potential of the battery, right? And so we have different amounts of charge that are going to deposit on capacitors that are in parallel with one another. The only way it would actually turn out to be the same is if they had the same value for the capacitance. Now, let's think about this, because remember, this is our goal. We want to know what's the equivalent resistance of two capacitors in parallel. And I'm setting all of this up so we can derive that relationship. Because here's the thing. The total amount of charge that leaves the battery is going to be determined by the overall capacitance of these two things combined together, right? That equivalent capacitance. And so we could say that the total amount of charge that comes out of the battery has got to be equal to that equivalent capacitance times the potential across the battery, right? Well, think about it though. the total charge that leaves the battery, it's going to have to be equal to the charge on capacitor 1, add it to the charge on capacitor 2, right? Charge is conserved. So if you've got a bunch of charge coming out of the battery, some of it's depositing down here on this plate, some of it's depositing over here on this plate, well, it may be splitting up, but the total, these two things added together, has still got to be equal to the total amount of charge that came out of the battery, right? So we could write this. The total charge has got to be equal to the charge on 1 plus the charge on 2. I mean, that's just conservation of charge right there. Charge can't be created or destroyed, so the overall amount is constant. So this is a relationship between the total charge that leaves the battery and the charge on both the plates. But now let's put in our expressions for each one, because the total charge is just this guy. So that's what I put over here, right? And then we found out that the charge on capacitor 1, well, here it's this. And the charge on capacitor 2 is this. All right? And so this is just that charge equation written in terms of the capacitances. But now think about it. We've got a common term in all of them. So I can divide out that delta V of the battery, get rid of it, and what I get left over is then that the equivalent capacitance is just going to be equal to capacitor 1 plus capacitor 2. Okay? So in other words, if I want to know what's the overall capacitance of this circuit, I just add C1 and C2 together if they're in parallel. And of course, I can generalize that out to any number of capacitors that are in parallel. So if I have N of them, then the equivalent capacitance is just going to be the sum of all the individual capacitors, right? So notice this is different than when they were in series. In series, you had to do that 1 over plus 1 over, and then add all that up and take it to the -1 power, right? Well, for parallel, you just add those things up. You know, and looking ahead, this is going to drive you crazy because you're going to have to remember this. But for resistors in series and parallel, they do exactly the opposite, okay? But we'll get to that. If you want to find the equivalent capacitance of a bunch of capacitors in parallel, just add them up. So let me show you an example. Say we have two capacitors. One of them is 2 picofarads. The other is 3 picofarads. They're in parallel with one another, and they're connected to a 12-volt battery. And the question is, what is the equivalent capacitance of the circuit? And then, when the circuit's fully charged, how much charge has left the battery and moved to the capacitors? Okay? Well, let's draw out our picture of our circuit. This is what it looks like. There's my battery. It's got 12 volts across it. Got capacitor 1 that's 2 picofarads. It's going to have its charge on it, Q1. Then I've got capacitor 2 that's 3 picofarads, and it's going to have its charge on it that is Q2. Okay, well, if we want to know the total amount of charge that's coming out of this, we need to know the equivalent capacitance. How do I get that? Just add the two things together, okay? And so I'm going to get 2 picofarads plus 3 picofarads. That's 5 picofarads. Well, now that I know the overall capacitance of this circuit, I can figure out how much charge is going to have to come out of the battery, okay? Because the total amount of charge coming out of that battery is going to be equal to the equivalent capacitance multiplied by the potential across the battery. That's our relationship, right? So let me plug in my numbers. Now be careful because, again, when I do my equations, I got to make sure I'm in farads. So pico is times 10 to the -12. So I got 5 times 10 to the -12. I'm going to multiply that by delta V. That's 12. And when I do that, I get 6 times 10 to the -11 coulombs. That's how much charge had to leak out of this battery before both of these things were fully charged up. Now, I do want you to know there is another way we could have figured out the total charge that left the battery. And that is, we could have found the charge on both of these. Because remember, the total charge has got to be equal to the charge on 1 plus the charge on 2, right? Well, the charge on 1 is going to be the capacitance of 1 times the voltage drop across it. Well, that's going to be 2 times 10 to the -12 picofarads, right? Times 12 volts, because we talked about it. The voltage across both the capacitors has to be equal to the voltage of the battery. So when I do the math here, I get 2.4 times 10 to the -11 coulombs. That's how much of the charge went on this plate. I can then find it for Q2. Q2 is going to be the capacitance of capacitor 2 multiplied by its voltage, right? So I get 3 times 10 to the negative 12 for my capacitance, 3 picofarads, so put in that times 10 to the minus 12, multiply that by 12 because it's still got to be the same voltage, and I get 3.6 times 10 to the negative 11 coulombs. Now, I can find my total charge because this charge, the Q1 and Q2, that's what came out of the battery. So if I want to know how much came out of the battery, I add the two things together, right? And when I do that, there's my charge on each one. Add those together, and look what you get. You get 6 times 10 to the negative 11 coulombs. You know, that's a way to check yourself right there on this problem, okay? But the thing is, when you have capacitors that are in parallel with one another, you want to get the equivalent capacitance just by adding them up. Now, that only works for capacitors that are in parallel. So we have two approaches now. When we have a string of capacitors in series, we have one way of getting the equivalent capacitance. And when we have a string of capacitors in parallel, we know how to get the equivalent capacitance there. And what we're going to look at next is, well, what do we do in a circuit that has a little bit of all of it? Okay, so you make sure you understand how to calculate equivalent capacitances for these two cases, purely series, purely parallel, because they're the pieces that we use to analyze more complicated circuits.